Chapter 8 L1X Architecture. This section provides a comprehensive architectural overview of the Layer1X network, delving into the underlying components and implementation details that drive its functionality. Components. The L1X network is comprised of several key components that would together enable its interoperability, scalability, and security. These components form the foundation of the network and ensure the smooth functioning of the Layer 1 smart contract protocol. The components of the L1X network include the following. Virtual machine. The L1X virtual machine is a powerful and efficient environment specifically designed for executing smart contracts on the Layer 1X blockchain platform. L1X innovates with WASM to eBPF compiler that improves the performance of L1X blockchain network at large scale. The L1X virtual machine utilizes eBPF bytecode interpreter and leverages the L1VM compiler infrastructure to optimize and compile smart contracts written in Rust. The L1X virtual machine consists of several key components, including the L1X Smart Contract Software Development Kit, also known as SDKs, L1X system calls, L1X SDK macros, L1X SDK, on-chain collections, and the core of the L1X virtual machine itself. The L1X Smart Contract SDK provides a comprehensive set of tools and libraries for developers, offering a higher-level abstraction and simplifying development process. It includes system calls for registry manipulation, storage operations, accessing execution content, and other essential functionalities. The SDK also supports on-chain collections, such as lookup maps, lookup set, and vector, which provide efficient storage options for large-scale data management within smart contracts. The L1X SDK macros further enhance the development experience by providing predefined functionality and convenient macros. The hash macro, for example, translates conventional Rust code into code that utilizes the primitives from the L1X syscrate. The L1X VM core serves as the foundation for executing eBPF bytecode in a secure and isolated environment. It performs two crucial steps: relocation and interpretation. During relocation, the VM analyzes the ELF sections of the eBPF file, including text instructions, data bytes, and function calls, and adjusts them accordingly. This process allows for efficient access to global variables and constant values. The interpretation stage utilizes a modified version of RBPF to handle non-standard extensions, enabling the execution of internal functions and ensuring compatibility with WASM. Thus, the L1X virtual machine provides a powerful and optimized execution environment for smart contracts on the Layer 1X blockchain. Its carefully designed components and robust infrastructure contribute to the efficiency, security, and scalability of the platform, empowering developers to build complex and innovative decentralized applications. Xtalk. Xtalk is a revolutionary cross-chain communication architecture introduced by L1X to enable secure exchange of smart contracts and facilitate interoperability across various blockchain networks. This architecture is designed with a decentralized approach, ensuring seamless asset and logic exchange across chains. By incorporating a blockchain-agnostic framework, Xtalk allows for efficient communication and interaction among multiple chains throughout the entire process. It leverages various components to handle tasks such as transaction identification, event validation, execution strategies, and transaction record keeping, ensuring the integrity and security of the system. With the integration of the L1X multisig smart contract, users can securely authorize cross-chain tokens and asset exchange, adding an additional layer of trust and reliability to the architecture. Overall, Xtalk represents a significant advancement in cross-chain communication, enabling a scalable and interoperable blockchain ecosystem. The topic has been further detailed in Xtalk. Full nodes. Full nodes play a crucial role in the L1X network by serving as the backbone for the transaction processing and maintaining the integrity of the blockchain. These nodes are responsible for introducing transactions into the L1X network and performing essential technical validations to ensure the accuracy and validity of transaction details. Beyond technical validations, full nodes also undertake non-technical validations to verify the logical correctness of the transactions. This step ensures that the transactions adhere to the predefined rules and conditions set by the L1X protocol. By performing these validations, full nodes contribute to the overall security and trustworthiness of the network. In addition to transactional validation, full nodes also act as block proposers. Through a random selection process, full nodes are assigned the responsibility of proposing new blocks to be added to the blockchain. The randomization mechanism ensures a fair and decentralized block creation process, enhancing the network's resistance to malicious attack and maintaining the decentralization principle. Furthermore, full nodes actively participate in the consensus mechanism of the L1X network. They validate and confirm the transactions that are proposed by other nodes, ensuring consensus on the state of the blockchain. This collective validation process helps achieve agreement among network participants and establishes the definitive state of the blockchain. The full node's contributions extend beyond transaction processing and consensus. They also play a crucial role in the overall maintenance and synchronization of the global state. By actively participating in block creation and verifying transactions, full nodes help ensure the consistency and integrity of the distributed ledger. Validator nodes. Validator nodes in the L1X network are integral to the transaction validation process, especially in the presence of mobile devices with limited computational capacity. These mobile nodes, serving as validators, contribute to the efficiency of transaction validation in L1X. The validator node assumes the responsibility of managing key components such as cluster registry management, cluster assignment randomizer, and aggregated cluster checkpoints. In the L1X network, validator nodes play a crucial role within the proof of X consensus mechanism. They establish synchronization with full nodes at specific intervals, ensuring the dissemination of up-to-date information regarding nodes in the cluster and similar clusters. This information is vital for full nodes, as it allows them to determine which node belongs to the same cluster before broadcasting blocks. By enforcing this mechanism, L1X mitigates the risk of malicious full node gaining control over the blockchain, enhancing the security and integrity of the network. The validator node's involvement in managing the cluster registry, which maintains information about participating nodes, ensuring the proper organisation and coordination of cluster assignments. Additionally, the cluster assignment randomizer algorithm contributes to the fairness and randomness in the selection of block proposers, further enhancing the decentralization aspect of the network. Another crucial responsibility of the validator nodes is the maintenance of aggregated cluster checkpoints. These checkpoints serve as a reference point for validating the blockchain's state and verifying the integrity of transactions. Validator nodes contribute to the creation and verification of these checkpoints, ensuring the consistency and reliability of the blockchain. By actively participating in the transaction validation process and maintaining essential components, validator nodes play a vital role in the overall functioning and security of the L1X network. Their involvement helps expedite transaction validation, leverages the capabilities of mobile devices, and strengthens the decentralization and integrity of the blockchain. Clustered databases. In the L1X blockchain network, clustered databases play a vital role in ensuring high availability, fault tolerance, and scalability to accommodate a large number of users. By utilizing multiple servers connected in a cluster, L1X effectively distributes data storage, enabling the database to handle a significant volume of transactions. The primary responsibility of clustered databases in L1X is to store user accounts and maintain a comprehensive record of all transactions. Each full node within the cluster synchronizes and maintains user accounts. facilitating data replication and ensuring data access even in the event of a few full nodes being unavailable. The replication technique enhances the network's fault tolerance and availability, safeguarding against potential single points of failure. One of the notable advantages of clustered databases is their ability to enable parallel processing, improving the overall performance of the L1X network. By leveraging parallelism, the network can process large datasets more efficiently, reducing latency and enhancing transaction processing speeds. This capability is crucial in meeting the scalability requirements of the blockchain, ensuring smooth and rapid transaction execution. By serving as the core component of the L1X architecture, clustered databases contribute to the robustness, reliability, and scalability of the blockchain network. They enable efficient data storage, replication, and parallel processing, ensuring high availability, fault tolerance, and optimal performance for a growing user base. Cluster Registry. The cluster registry stores and maintains essential information about the full nodes within a cluster. It serves as a repository for storing details such as the current state of each node, IP addresses, metadata, and other relevant information necessary for efficient communication and coordination among full nodes. One of the primary responsibilities of the cluster registry is to ensure correct data storage and processing within the L1X network. By maintaining up-to-date information about the nodes in the cluster, the registry enables efficient routing of data and transactions, facilitating seamless communication and collaboration among the participating nodes. By providing a vital source of information, it streamlines the process of data synchronization and facilitates efficient decision-making within the network. The cluster registry enables full nodes to access the latest information about other nodes in the cluster, ensuring smooth coordination and consensus during block creation and transaction validation. The cluster registry also enhances the fault tolerance of the L1X network. In the event of a node failure or disruption, the registry can facilitate the redistribution of tasks and responsibilities among the remaining nodes in the cluster, ensuring continuity of operations and mitigating the impact of potential single points of failure. Cluster Register Management. Cluster Register Management ensures the seamless integration and coordination of nodes within the cluster. Its primary role is to maintain accurate and up-to-date information about the full nodes in the cluster, including the status, availability, and other relevant details. By monitoring the cluster and updating the registry accordingly, Cluster Register Management enables efficient cluster operations and contributes to the high availability and robustness of the L1X blockchain. The responsibilities of Cluster Register Management encompass two key aspects. Firstly, it involves continuous monitoring of the nodes within the cluster to track the status and detect any changes such as node additions, departures, or failures. This real-time monitoring ensures that the cluster register remains synchronized with the dynamic nature of the network, allowing for accurate representation of the active nodes at any given time. Secondly, Cluster Register Management is responsible for updating the cluster registry based on the detected changes in the cluster. When a new node joins the cluster, the management component adds its information to the register, ensuring its inclusion in the network operations. Conversely, if a node leaves the cluster or encounters any issues, the management component removes or updates its entry in the registry accordingly. These updates guarantee that the cluster register accurately reflects the current state of the cluster and enables effective communication and coordination among the nodes. Cluster Register Management contributes to the overall efficiency, reliability, and availability of the L1X blockchain network. By maintaining an up-to-date and accurate register of the full nodes, it enables seamless communication and collaboration within the cluster, facilitating efficient transaction processing and consensus mechanism. Additionally, Cluster register management ensures fault tolerance by promptly detecting and responding to the node failure or departures, allowing the network to adapt and redistribute tasks as needed. Cluster Assignment Randomizer. Cluster Assignment Randomizer ensures proper load balancing and even distribution of nodes across clusters. Its primary responsibility is to randomly assign nodes to different clusters based on factors such as the total number of nodes, total number of clusters, and the nodes already present in each cluster. By distributing the nodes evenly, the Cluster Assignment Randomizer helps maintain optimal performance and prevents any single cluster from becoming overloaded, which could potentially degrade the network's efficiency. This load balancing mechanism ensures that the processing power and resources are effectively utilised across the clusters, enhancing the overall scalability and performance of the L1X blockchain. One significant advantage of the Cluster Assignment Randomizer is its contribution to the security of the L1X blockchain. By randomly assigning nodes to clusters, it becomes challenging for attackers to target a specific cluster and disrupt its operations. The dynamic creation of clusters after certain intervals with a random combination of available full nodes further adds an additional layer of security. The randomization makes it difficult for attackers to predict the composition and structure of clusters, thereby bolstering the network's resilience against malicious activities. Cluster Assignment Randomizer optimizes the network's performance, ensures fair distribution of nodes, and enhances the overall security of the L1X blockchain. By intelligently assigning nodes to clusters, it enables efficient resource utilization, load balancing, and reduces the vulnerability to targeted attacks. This mechanism reinforces the scalability, robustness, and integrity of the L1X blockchain network, contributing to its overall reliability and trustworthiness. Cross-cluster messaging. Cross-cluster messaging facilitates seamless communication and coordination among nodes located in different clusters. Its primary purpose is to enable the exchange of data and transactions involving different clustered databases within the L1X network. In the context of L1X, cross-cluster messaging ensures that transactions related to different clustered databases can be securely transmitted between clusters without compromising the integrity of the data. This is achieved by applying digital signatures to the transactions, guaranteeing their authenticity, and protecting them from unauthorized modifications during transit. To maintain optimal network performance as the volume of cross-cluster transactions increases, L1X implements efficient routing and processing algorithms. These algorithms ensure that the messages are routed accurately and processed swiftly, minimizing latency and maximizing throughput. By optimizing the routing and processing of cross-cluster transactions, L1X achieves scalability without compromising the network's overall performance. By enabling seamless communication between clusters and facilitating the exchange of transactions involving different cluster databases, it promotes interoperability and expands the scope of use case that can be supported by the L1X blockchain. Moreover, cross-cluster messaging ensures that L1X blockchain can handle increasing transaction volumes without sacrificing network performance or introducing significant delays. This feature is particularly crucial in scenarios where multiple clusters are involved, allowing for the parallel processing of cross-cluster transactions and minimizing the impact on overall transaction throughput. Aggregated cluster checkpoint. The aggregated cluster checkpoint ensures the synchronization and integrity of the blockchain data among numerous full nodes within a cluster. It addresses the challenge of maintaining consistency and data integrity in the presence of node failures or network issues. In L1X, each full node in a cluster may operate in a different state, and to ensure synchronization across all nodes, the concept of cluster checkpoints is introduced. The aggregated cluster checkpoints serve as a consolidated record of the last updated timestamp for each full node within the cluster. It collects and combines individual checkpoints from all full nodes, creating a single, unified checkpoint that represents the latest state of the blockchain data within the cluster. The primary responsibility of the aggregated cluster checkpoint is to safeguard against data loss and maintain the consistency of the L1X blockchain in the event of full node failures or network disruption. By consolidating the individual checkpoints, it provides a reliable reference point for verifying the integrity and consistency of the blockchain data across different full nodes within the cluster. Aggregated cluster checkpoint ensures the resilience and reliability of the L1X blockchain network. In the event of a full node failure or network issue, the aggregated checkpoint serves as a recovery mechanism, allowing the network to recover and restore data integrity efficiently. By tracking and maintaining the last updated timestamp for each full node, it enables the network to identify any discrepancies and initiate the necessary measures for data synchronization. Furthermore, the aggregated cluster checkpoint enhances the overall security of the L1X blockchain by ensuring that no single full node can unilaterally manipulate the blockchain data within the cluster. It acts as a consensus mechanism that ensures the consistency of the blockchain state across different nodes, reducing the risk of malicious activities and ensuring the trustworthiness of the network. Thus, the aggregated cluster checkpoint maintains the synchronization, integrity, and consistency of the blockchain data among multiple full nodes within a cluster. Stake registry. The stake registry serves as a record-keeping mechanism for staking activities and token ownership. It plays a significant role in facilitating the POX consensus mechanism and ensuring the integrity and transparency of the staking process. The dynamic ceiling allocation mechanism in L1X adjusts the maximum amount of tokens that can be staked by participants based on various factors, such as network demand, token supply, and overall network conditions. This dynamic adjustment allows for optimal utilization of network resources while maintaining the stability and security of the blockchain. In L1X, full nodes participate in the consensus by staking L1X tokens. The stake registry maintains detailed information about the staking activities performed by full nodes. It includes essential details such as the number of tokens staked, the time of the staking, rewards earned on the staked tokens, and other relevant information associated with the staking full nodes. One of the primary responsibilities of the staking registry is to provide an accurate and up-to-date record of token ownership within the L1X blockchain. By tracking the staked tokens and their corresponding ownership details, it enables the network to establish the rightful stakeholders and their influence on the consensus process. This promotes a fair and decentralized approach to governing the blockchain network. Moreover, the stake registry serves as a foundational element for implementing slashing and reward mechanisms in L1X. It enables the network to enforce penalties, such as slashing a portion of staked tokens in case of malicious behavior or protocol violations. Conversely, it also facilitates the rewards of staked nodes for their active participation and contribution to the consensus. This dynamic allocation of staked value ensures a balanced distribution of tokens across the network, preventing centralization and promoting decentralization and security. Ensuring the security, transparency, and accountability of the staking process within the L1X blockchain network is the key responsibility of the stake registry. By utilizing a distributed database system replicated across all full nodes, it enhances data availability, resilience, and tamper resistance. This ensures that the ownership record and staking details remain consistent and verifiable across the network. Additionally, the stake registry promotes the economic incentives and governance aspect of the L1X blockchain. It encourages active participation from stakeholders by providing a mechanism to stake the tokens, earn rewards, and influence the consensus process. This fosters a healthy ecosystem where participants are incentivized to act in the best interest of the network's growth and stability. Mobile node syncing. Mobile node syncing is the process where mobile devices synchronize with the cluster registry and maintain an updated state of the cluster. It ensures the efficiency, coordination, and robustness of the L1X blockchain ecosystem. This process facilitates the coordination among full nodes for consensus and maintains correct data storage and processing within L1X network. By synchronizing with a cluster registry, mobile nodes gain access to the latest information about the cluster, including node states, IP addresses, metadata, and other essential details required for effective communication among full nodes. In the L1X blockchain, the incremental syncing mechanism is employed to optimize the syncing process for mobile nodes. Instead of updating the entire cluster registry, the incremental syncing mechanism focuses on transmitting only the modified entries or updates. This approach is particularly beneficial for mobile devices with limited processing power, as it minimizes the computational burden while ensuring that mobile nodes stay updated with the latest state of the cluster. The role of mobile node syncing extends beyond mere information retrieval and storage. It contributes to the overall stability and resilience of the L1X blockchain network. By actively participating in the syncing process, mobile nodes strengthen the network's robustness, especially in adverse scenarios where stable connections may be challenging to maintain. The involvement of a large number of mobile nodes enhances the network's ability to withstand potential disruptions and ensure a more distributed and resilient consensus mechanism. Furthermore, mobile node syncing aligns with the core design principles of the L1X blockchain, which emphasize decentralization, efficiency, and adaptability. By allowing mobile devices to synchronize within the cluster registry and participate in the consensus process, L1X promotes inclusivity and leverages the collective power of a diverse range of devices. This approach enhances the network efficiency, scalability, and ability to handle a large volume of transactions. Consensus mechanism. The L1X blockchain utilizes a two-tiered hybrid consensus mechanism known as POX, or Proof of X, to achieve consensus among decentralized nodes regarding transaction validity and chronological order. This innovative approach incentivizes both active participation and stakeholding, striking a balance between the interest of users and stakeholders. It represents a forward-thinking and dynamic method of consensus building within the L1X network. In the L1X POX consensus, mobile devices with limited computation and memory capacity are empowered to actively participate in the consensus process by continuously tracking and sharing the latest state of the blockchain. This inclusive approach allows even more devices to contribute to the consensus, enhancing the overall decentralization and resilience of the network. Meanwhile, full nodes within the L1X blockchain play a critical role in consensus by holding and staking L1X coins. By staking their tokens, these nodes demonstrate their commitment to the network and earn the right to validate transactions and propose new blocks. This stakeholding mechanism ensures that participants with a vested interest in the network have influence over the consensus process. The design principles of the L1X blockchain, coupled with the POX consensus mechanism, offer several advantages. Firstly, it incentivizes active participation from both mobile devices and full nodes, fostering a more inclusive and diverse network. Secondly, it balances the interest of users and stakeholders, promoting fairness and transparency in consensus building. Lastly, this dynamic approach allows for the adaptability and scalability as the network grows, ensuring its long-term viability and effectiveness. L1X consensus mechanism working. Transactions in byte format, such as RLP, are received by L1X full nodes through the RPC. The full nodes append a receival timestamp to the transactions before initiating transaction authentication. During this authentication process, various aspects of the transaction, including its structure, balance efficiency, addresses, and digital signature, are meticulously verified. Once authenticated, an authentication timestamp is added and the transaction is forwarded to the mempool. The mempool, or memory pool, serves as a storage mechanism for unconfirmed transactions. In L1X, user accounts are partitioned into clustered databases to enhance efficiency. Each clustered database holds the account states for a specific subset of users. Mobile nodes maintain the cluster registry, which maps account records to the corresponding full nodes. By periodically synchronizing the cluster registry from mobile nodes, the full nodes ensure that up-to-date information is available. Leveraging the cluster registry, the mempool identifies the relevant clusters and the associated full nodes that hold the clustered databases containing the account records relevant to the transaction. The transaction is broadcast to all the pertinent cluster nodes. Subsequently, these nodes perform non-technical validation, an essential step involving the verification of smart contracts, adherence to predefined rules, testing edge cases, and confirming transaction accuracy. This validation process ensures the overall integrity of the blockchain. Beyond the clustered databases and cluster registry, full nodes also maintain the state registry. The state registry records which full nodes have state tokens to participate in the consensus and proposed blocks. This information is stored locally within each full node. Random selection of a block proposer ensures true randomization outcomes while maintaining privacy by applying homomorphic encryption to node identities. The chosen block proposer constructs the block and applies zero knowledge proof, or ZKPs, to enable succinct and fast verification of block. The block, along with the ZKP proof, is exclusively broadcasted to the relevant cluster nodes. Full nodes validate the integrity or correctness of block with much smaller proof sizes and transmit it for further validation. In cases where a transaction involves accounts across different clustered databases, cross-cluster messaging is employed to facilitate data sharing. The aggregated cluster checkpoint plays a pivotal role in this process by maintaining the last updated timestamp for each full node's clustered database. Regular synchronization between full nodes and mobile nodes ensure that the clustered databases and aggregated cluster checkpoint remain consistently updated. The implementation of hierarchical temporal memory enables real-time detection of malicious nodes by identifying abnormal transaction patterns. This robust security mechanism is applied both during the transaction submission phase and when blocks are broadcast across the network, actively safeguarding the L1X blockchain network against malicious activity. The consensus mechanism of the L1X blockchain thus employs multiple stages including transaction authentication, non-technical validation, block proposal, and data synchronization. These stages, combined with techniques like homomorphic encryption and hierarchical temporary memory, ensure that integrity, security, and privacy of the L1X blockchain network, providing a robust and trustworthy decentralized ecosystem. Block proposer selection, true randomization, and homomorphic encryption. In the L1X blockchain, the process of selecting a block proposer plays a critical role in maintaining the security and fairness of the network. The block proposer is responsible for creating and adding new blocks to the blockchain, contributing to the overall consensus mechanism. To ensure the integrity and robustness of the blockchain, a randomized algorithm is employed for the selection of the block proposer. POX consensus metrics. In the quest for achieving consensus and decentralization, the participation of network participants holds the utmost importance. Trust in the L1X blockchain network and the availability of trusted participants are crucial factors that drive the success and sustainability of the blockchain ecosystem. To address this, a mechanism that efficiently considered both old and new participants in the POX consensus is approved. By incorporating metrics such as stake score, kin score, and X score, we aim to evaluate participants' stake holdings, active involvement, and adherence to security measures. These metrics play a vital role in achieving consensus, promoting decentralization, and ensuring the integrity and security of the network. In the subsequent sections, we will delve into the significance of each metric, highlighting their importance in maintaining a robust and reliable POX consensus mechanism. State score. This is a measure of a node's commitment to the network, based on the amount of L1X coins they have staked, the length of time they have been staking, and the length of time they have agreed to lock up their coins. A high state score indicates that a node is more likely to behave honestly, as they have more to lose if they are caught cheating. Kin score. This is a measure of a node's reliability and trustworthiness based on their uptime, participation history, response time, and security measures. A high kin score indicates that a node is more likely to be able to participate in the consensus process reliably and without disruption. X score. This is a combined measure of state score and kin score, which is used to determine which nodes are eligible to participate in the POX consensus. A higher X score indicates that a node is more likely to be a reliable and trustworthy participant in the consensus process. The POX consensus metrics are designed to achieve consensus and decentralization by rewarding nodes that are committed to the network, reliable and trustworthy. By ensuring that the network is sufficiently decentralized, the POX consensus helps to protect the network from attack and shows that it is fair and transparent. POX consensus process. X score, state score, and kin score are integral components of the sophisticated block proposer selection process in the L1X blockchain ecosystem. Page 47, there is a flow diagram. Figure 2 of the POX consensus process. To calculate X score, the process considers all nodes that have staked a minimum balance and are actively available within the network. These nodes undergo evaluation to determine their X score, which subsequently plays a significant role in determining their eligibility for the next epoch of the consensus process. Nodes with an X score exceeding the defined X score threshold, that varies based on the network dynamics, are deemed eligible for participation. To ensure data privacy and security, homomorphic encryption is applied to X score. This cryptographic technique enables computations to be performed on encrypted data without compromising its confidentiality. By leveraging homomorphic encryption, the privacy of X score calculations is preserved, allowing for a secure evaluation process. Furthermore, a randomized algorithm is applied to the homomorphically encrypted X scores. This algorithm introduces an element of randomness in the selection of the block proposer. By employing a randomized approach, the consensus protocol mitigates potential biases and ensures a fair and decentralized block proposer selection process. Overall, the intricate interplay between X score, state score, kin score, homomorphic encryption, and randomized algorithms forms a robust framework that enables accurate evaluation, privacy preservation, and fair selection within the L1X blockchain network. The randomness injected into the selection process prevents any undue advantage or bias towards specific nodes, fostering a level playing field for all participants. Furthermore, the use of homomorphic encryption ensures that the privacy of the nodes is preserved, enhancing the overall security posture of the L1X blockchain. POX mathematical model. Multi-objective optimization is a fundamental concept in mathematical optimization that involves optimizing multiple objective functions while considering a set of constraints. In the context of blockchain consensus, the state score, kin score, and X score calculation problem can be viewed as a multi-objective optimization problem. This problem aims to simultaneously optimize groups of conflicting objectives in order to achieve an optimal solution. So chapter 8.2.3 is the POX, the proof of X mathematical model. Now I'm going to skip over this and go to chapter 8.2.4 purely because there's too much mathematics within this chapter to read it and comprehend it, understand it. It's something that you've probably got to read, and obviously if you're a mathematician you'll understand it, but for the best part it's probably not something you comprehend. Not something I do anyhow. So chapter 8.2.4, Zero Knowledge Proof. The block proposer applies zero knowledge proof, ZKPs, on the block created and then broadcasts it into the network. Applying ZKP to the block before broadcasting it to the network serves multiple purposes. It ensures the integrity and correctness of the block by verifying that it adheres to the predefined rules and structure of the blockchain. This prevents the inclusion of invalid or malicious transactions in the block, enhancing the overall security of the network. The application of ZKP in the L1X blockchain also leads to improved network efficiency. Since the block undergoes ZKP before broadcasting, the size of the block is significantly reduced. The reduction in block size enables faster transmission and lower latency within the network. Consequently, the overall performance and scalability of the L1X blockchain are enhanced, allowing for a smoother and more efficient consensus process. Malicious node detection, hierarchical temporary memory. Hierarchical temporary memory is a powerful machine learning algorithm renowned for its ability to identify anomalies in temporal patterns. In the context of blockchain technology, where maintaining security is of our utmost importance, HTM serves as a valuable tool for detecting and mitigating malicious activities within the network. Malicious nodes in a blockchain network often exhibit abnormal behavior over time, such as initiating fraudulent transactions or generating an unusually high volume of transactions. By leveraging the capabilities of HTM, these behavioral patterns can be analysed to identify deviations from the norm. HTM excels at processing large volumes of transactions in real time, making it an ideal solution for monitoring the activities of all nodes within the network. One of the significant advantages of HTM is its ability to learn and adapt to changing behavioural patterns, including newly emerging attack techniques. As the blockchain landscape evolves, attackers continuously devise new strategies to exploit vulnerabilities. HTM's adaptability enables it to recognise and respond to these evolving threats, thereby bolstering the security and resilience of the L1X blockchain. The integration of HTM within the L1X blockchain plays a crucial role in identifying malicious nodes by promptly detecting anomalies in their behaviour. By applying HTM at two key stages, the transaction entry point and the block broadcasting stage, L1X ensures comprehensive coverage and robust security throughout the blockchain network. At the transaction entry point, HTM analyses incoming transactions, allowing for the immediate detection of suspicious or fraudulent activities. This early detection capability prevents potentially harmful transactions from entering the network, mitigating the risk of security breaches. Similarly, HTM is employed when blocks are broadcast to nodes with the network. By analysing the temporal patterns of block propagation and processing, HTM can identify any irregularities or deviations from expected behaviours. This enables the system to take appropriate measures to address potential threats and maintain integrity of the blockchain. As a result, HTM serves as a critical component in upholding the security and trustworthiness of the L1X blockchain ecosystem. Benefits. The POX consensus mechanism offers a multitude of advantages in achieving genuine decentralization while ensuring a secure and scalable blockchain infrastructure capable of high throughput as listed below. Number 1. Efficient transaction validation. The POX consensus mechanism in L1X reduces energy consumption by eliminating the need for high computational power, resulting in a more sustainable blockchain network. Number 2. Scalability through active micro-device participation. With POX, the network scalability is maintained even as the number of validators increases. The active engagement of micro-devices ensures consistent network performance, accommodating a growing user base. Number 3. Pure decentralization. POX enables a purely decentralized network by actively involving micro devices in the consensus process. The random selection of block proposer ensures fairness and prevents any single or group of nodes from gaining unfair advantage. Number 4. Enhance security and privacy through ZKP. L1X applies ZKP on blocks before broadcasting them, ensuring the correctness of blocks while preserving sensitive transaction information. ZKP enhances security by reducing the block size, enabling faster transmission, and minimizing the risk of data exposure. Number 5. Enhanced privacy through homomorphic encryption. Utilizing homomorphic encryption to protect the privacy of full node identities during consensus brings significant advantages to the blockchain ecosystem, as it ensures that the selection process remains secure and unbiased while maintaining the confidentiality of node participants. By encrypting identities and applying a randomization algorithm, the blockchain network enhances privacy and prevents malicious entities from manipulating the selection process. Number 6. Proactive detection of malicious nodes. The utilization of HTM in L1X allows for the real-time identification of anomalies and abnormal transaction patterns associated with malicious nodes. HTM's ability to handle large transaction volumes and adapt to emerging attack patterns strengthen network security. Number 7. Protection against targeted attacks. Random selection of block proposers make it difficult for attackers to target specific nodes. This additional layer of security ensures the integrity and resilience of the L1X blockchain network. Number 8. Robust network integrity. By combining transaction authentication, non-technical validation, data synchronization, and security measures, the POX consensus mechanism in L1X ensures the overall integrity and reliability of the blockchain network. These benefits collectively contribute to a more efficient, scalable, and secure decentralized blockchain ecosystem in L1X. By reducing energy consumption, promoting scalability, preserving privacy, and detecting and preventing malicious activities, the POX consensus mechanism enables the L1X blockchain to meet the demand of a growing network while maintaining a high level of security and integrity.